Continuous-Time Fourier Transform, visualizing its properties. This project presents a visual exploration of the fundamental properties of the Fourier transform. Each concept is introduced through its mathematical expression and illustrated with dynamic animations that connect the time and frequency domains. Through these visualizations, we aim to build an intuitive understanding of how signals transform and interact across both representations. Linearity property. The mathematical expression is shown below. This property states that linear combinations in time remain linear in frequency. Next, we will see a visual explanation of how signals combine and how their spectra behave accordingly. In this animation, we explore the linearity property of the Fourier transform. We begin with two independent signals. The first signal is a rectangular pulse, and the second is a double exponential function. Their corresponding Fourier transforms are shown on the right. Now, we introduce a linear combination of both signals. Coefficients A and B control their relative contribution. Observe how modifying these coefficients changes the combined signal. At the same time, the frequency domain representation changes in exactly the same way. This demonstrates that the Fourier transform is a linear operator. The transform of a sum is equal to the sum of the transforms. Time shifting property. The mathematical expression is shown below. Shifting a signal in time does not change its magnitude spectrum, only its phase. Next, we will visualize how this delay affects the frequency domain representation. We now explore the time shifting property of the Fourier transform. The original signal is a double exponential function. Its Fourier transform is purely real and shown on the right. Now we shift the signal in time by a parameter t0. Shifting in time does not change the magnitude of the spectrum. Instead, it introduces a phase rotation. This appears as a twisting of the curve in the complex frequency domain. Time shifts correspond to complex exponential modulation in frequency. Frequency shifting property. The mathematical expression is shown below. Modulating a signal in time shifts its spectrum along the frequency axis. Next, we will observe how oscillations in time translate into spectral displacement. We now explore the frequency shifting property of the Fourier transform. The original signal is a double exponential. Its spectrum is centered at zero frequency. Now we multiply the signal by a complex exponential. This introduces oscillations in time. Observe that this modulation shifts the spectrum along the frequency axis. The shape of the spectrum does not change. It only translates rigidly in frequency. This demonstrates that multiplication by a complex exponential in time corresponds to frequency shifting. Time scaling property. The mathematical expression is shown below. Compressing or expanding a signal in time produces the opposite effect in frequency. Next, we will see how time scaling stretches or compresses the spectrum. We now explore the time scaling property of the Fourier transform. The original signal is a double exponential function, with its spectrum shown on the right. When the signal is compressed in time, its spectrum expands in frequency. When the signal is stretched in time, its spectrum becomes more concentrated. Notice also that the amplitude scales inversely with the scaling factor. This illustrates the inverse relationship between time and frequency domains. time reversal property. The mathematical expression is shown below. Reversing a signal in time reflects its spectrum across the frequency axis. Next, we will visualize how this symmetry appears in both domains. We now explore the time reversal property of the Fourier transform. The original signal is a causal exponential decay, defined only for positive time. Now we progressively reverse time. The signal flips from right-sided to left-sided. In the frequency domain, this corresponds to a reflection of the spectrum. Notice how the complex structure is mirrored across the frequency axis. This shows that reversing time results in reversing frequency. Duality property of the Fourier transform. The mathematical expression is shown below. Time and frequency domains are interchangeable under specific transformations. Next, we will see how swapping roles reveals deep symmetry between both representations. We now explore the duality property of the Fourier transform. We begin with a rectangular pulse in time, and its corresponding sync spectrum in frequency. Now, we apply the duality transformation. The roles of time and frequency are exchanged. The time domain now contains the sync function, while the frequency domain becomes a scaled and mirrored rectangular pulse. This shows that the Fourier transform has a deep symmetry between time and frequency. Duality reveals that these domains are interchangeable representations of the same structure. Differentiation in the time domain. The mathematical expression is shown below. Differentiating a signal emphasizes rapid variations and corresponds to multiplication in frequency. Next, we will visualize how this operation modifies both shape and spectrum. We now explore the time differentiation property of the Fourier transform. The original signal is a Gaussian function, which is smooth and symmetric. Similarly, its Fourier transform, depicted on the left, is also a Gaussian signal. Now we take its time derivative. Notice how the signal becomes antisymmetric. In the frequency domain, differentiation corresponds to multiplication by j omega. This introduces a phase shift and amplifies higher frequencies. This shows that differentiation enhances rapid variations in the signal. Differentiation in the frequency domain. The mathematical expression is shown below. Multiplying a signal by time corresponds to differentiating its spectrum. Next, we will observe how this operation reshapes the frequency domain. We now explore the frequency differentiation property of the Fourier transform. The signal is defined through its frequency representation, which is a Gaussian. Multiplying the signal by time corresponds to differentiating its spectrum. Notice how the spectrum develops zero crossings and changes shape. Higher powers of time correspond to higher order derivatives in frequency. This demonstrates a deep duality between time multiplication and frequency differentiation. Integration in the time domain. The mathematical expression is shown below. Integrating a signal accumulates its values and smooths variations. Next, we will see how this affects the spectrum, especially near zero frequency. We now explore the time integration property of the Fourier transform. The signal is a finite sine pulse defined over the interval from -1 to 1 and 0 elsewhere. We now compute its cumulative integral from -infinity up to time t. Observe how the signal accumulates smoothly, building up structure over time and then returning to zero. In the frequency domain, integration corresponds to division by j omega, which modifies both magnitude and phase. This operation emphasizes low-frequency components while attenuating higher frequencies. Convolution in the time domain. The mathematical expression is shown below. Convolution describes how a system modifies an input signal over time. Next, we will visualize how sliding and overlapping signals produce the output. We now analyze convolution in a causal system. The input signal is a shifted triangular pulse, ensuring that it exists only for positive time. The system is defined by a causal exponential response. Convolution is computed by sliding the impulse response across the input. The output builds as the overlap between both signals increases. In the frequency domain, each signal has its own spectrum. The time shift introduces a phase rotation in the input spectrum. The exponential response acts as a low-pass filter. Their product produces the output spectrum, combining filtering and phase effects. Convolution in the frequency domain. The mathematical expression is shown below. Multiplication in time corresponds to convolution in frequency. Next, we will see how spectra combine through a sliding and accumulation process. We now explore convolution in the frequency domain. We begin with two spectra: a Gaussian signal and a shifted Gaussian kernel. Instead of multiplying, we now perform convolution in frequency. This is done by sliding one spectrum across the other, multiplying and integrating at each position. Observe how the output spectrum builds progressively as overlap increases. In the time domain, this corresponds to multiplication of signals. Frequency convolution reveals how spectral components interact to produce modulation effects. This duality between multiplication and convolution is fundamental in signal processing. Even and odd signal properties. The mathematical expression is shown below. Symmetry in time determines the structure of the spectrum. Next, we will observe how even signals produce real spectra and odd signals produce imaginary ones. We now explore symmetry properties of the Fourier transform. We begin with an even signal, a Gaussian function symmetric about the origin. Its Fourier transform is purely real and also symmetric in frequency. Now we introduce an odd component, creating an antisymmetric signal. Observe how the spectrum transitions from purely real to purely imaginary. Even signals produce real spectra, while odd signals produce imaginary spectra. This reveals a deep connection between symmetry in time and structure in frequency. These properties are fundamental for understanding signal decomposition. Parseval's relation. The mathematical expression is shown below. This relation shows that energy is preserved between time and frequency domains. Next, we will visualize how energy is distributed and conserved across both representations. We now explore Parseval's relation using energy interpretation. At the top, we show energy density in time and frequency, given by the squared magnitude of each signal. At the bottom, we accumulate this energy, integrating from the center outward in both domains. Notice how the total energy grows symmetrically, expanding from the origin. Most importantly, both accumulated energies remain equal at all times. This confirms that total energy is preserved between time and frequency domains. And be not conformed to this world, but be ye transformed by the renewing of your mind, that ye may prove what is that good, and acceptable, and perfect will of God. Romans 12 verse 2.